Good day, colleagues. Thanks to Professor Cherednichenko for the invitation to this conference, especially in this lonely time when we don't get enough social interaction with other people. And I noted the somewhat informal nature of this conference, relaxed, nice nature. So in theme of it, I changed up my title just a little bit to reflect that kind of in that kind of nature. And I in the title I label our reaction an incredible reaction, a little bit boastful and a little bit bold in the American tradition. But I hope by the end of this talk to really prove to you that it really is an incredible reaction that we've come across, and that exploratory chemistry really is one of the more exciting parts of doing this kind of work. So this whole talk is kind of a little bit of a journey into catalysis, because we really did not initially even think this problem would be about catalysis, but it ended up being completely focused on catalysis. And this journey begins in 2015 when my future boss, Dr. Jenna in VCU, they discovered computationally, this has not been synthesized yet, they discovered a new carbon allotrope, and they called it pentagraphene. This discovery did get some press from Popular Science news, so we can see here that it was kind of a small phenomenon. People were excited about this, and this paper has since gotten 600 citations, so it's quite somewhat of a hot topic. And what is pentagraphene? Well, pentagraphene, first of all, they discovered that it is a semiconductor, and the way Puru describes the discovery is they were sitting at a restaurant when they saw these Cairo tiles. These tiles are very common in Egypt, I'm told. And the feature that describes this kind of tile is, of course, that it is made up completely of pentagons, right? Of five-sided shapes. So when we analyze the Cairo tile, we see that the pentagons are all part of two hexagons that are stretched, right? This one is part of this hexagon and also this hexagon. So from a logical point of view, it seems like this kind of material could exist made up of purely carbon, because it's still ultimately like it's ultimately still like graphene, but it's made up, the hexagons individually are made up of pentagons. So it seemed plausible. It seemed plausible that this is possible, and they calculated it. And of course, the commonsensical thing that happened is that this is not a completely flat surface. And the reason for that is, if we think about fullerene, the points of curvature are, of course, the pentagons, and the surface is, of course, then kind of filled with kinks. So it's a kind of a bumpy surface when analyzed. So this is their final result. They did molecular dynamics to show that it is stable, but of course we know that molecular dynamics are not a direct proof of stability. You have sometimes the instability happens way beyond the time scales available to molecular dynamics. And at that time, I was a graduate student under the Nobel Prize winning Harold Kroto, and his first reaction to this discovery was, "I don't like it." And of course, he discovered the C60 allotrope fullerene. And the first thing he did immediately was he got his friends, his computational chemist friends, he assembled a team, and they published a paper where they definitively proved that pentagraphene is at best a metastable material. And they even contended that it is a completely unstable material, but it probably is metastable. So the way they basically proved it, and the reason I contend that it's still metastable, is the phonon modes were still all real, so it wasn't a transition state, but it might not be a very deep local minimum. And this is kind of the mechanism they showed where it opens up into graphene, and that's why it's unstable, is because it's a very exothermic reaction. So that was their conclusion. And the other thing to note about pentagraphene is, of course, that it's actually a mixed surface. It's made up of tetrahedral sites and trigonal planar sites. Of course, sp3, as we recall from Chemistry 101, prefers a carbon prefers a tetrahedral configuration, and then sp2 carbon prefers a trigonal planar configuration. Of course, graphene is all sp2, and this is a mixed surface, and that's where the kinks come from, is from sp3. Unfortunately, tetrahedral means that these kinks that happen makes the material reactive as well, and it in fact also gets easily oxidized. The other thing that has been proposed, and this has been researched a lot because there is still a lot of excitement for this material, is that it could be a gas sensor, because of course you have a lot of hanging bonds on the surface, and they could attach all kinds of gas molecules. So that was the idea. And this is where I come in. In 2017, I get hired by Professor Jenna, and he is still convinced that this material must be possible to synthesize somehow. And it is my job to propose how, to work with an experimental group and propose how are we going to do this. Well, the material is metastable, but we should still be able to synthesize it at least in its encapsulated form. Of course, if we synthesize it that way, it might not be a semiconductor then, but that is our hope, is that at least we can synthesize it that way. And maybe we could try to grow it on a catalytic, for example, copper surface at a high temperature by choosing the correct precursors. So this was the first idea, and this was, of course, a very unlikely idea of making a metastable material under high temperature. It seems unlikely. They tried it, and I don't think it worked. So it was back to the drawing board. Well, this is where the chemical approach comes in. We could maybe somehow devise a reaction where we have homocoupling or heterocoupling, and quite possibly we could make the metastable material. This is quite normal in chemistry, because we know, for example, a good example of this is DMMP. In experiment, they always make 5. So the way they devise the reactions, they always get the isomer number 5. And it's actually it's actually much less stable than the global minimum, which is this one, and then 2 is also quite stable. So this is quite plausible. Now comes the hard part. How are we going to do it? So of course I didn't have a lot of experience in catalysis, so I just started looking through literature kind of randomly, trying to walk into the solution to this problem and try to somehow solve it. So the first thing I noted was fluorographene. Fluorographene is tetrahedral because the fluorines, of course, sit on top of the carbon centers, and so we produce kinks just like in pentagraphene. My boss didn't like this very much because he wanted the pure allotrope, but ultimately I was also by this point convinced that the pure allotrope is unstable, and we need some kind of other. We need to cover it with something to stabilize it. So of course I believe that it is possible to create this material. Maybe even we don't have to completely coat it, but at this point I did not believe we could completely create the material as devised originally. And this led me to another interesting paper, a very important paper as it turns out, where they show this kind of new compound, this new catalyst, where they have a magnesium-magnesium bond. And this magnesium-magnesium bond is capable of stripping off a fluorine off a perfluorine ring. So if you look closely right here, this perfluorobenzene ring is actually floating above this complex, and then it takes off the fluorine, and then the complex is without the fluorine, so it's ready to react with something else. So this is where the coupling could happen. And here's in 3 dimensions how this looks. This is the transition state 1. And the reason this is kind of interesting is magnesium dimers, of course, are very unstable. And if you look at it from the perspective of molecular orbital theory, it's very easy to understand. we have two completely filled free s2 orbitals, which create a completely filled sigma molecular orbital, and then a completely filled sigma star molecular orbital. Now, when we add some kind of groups which pull electron density away from the magnesiums, of course, we pull some of this sigma star density away, and that, of course, creates a bond. The bond is actually an order of magnitude stronger than the dimer, which is basically just a dipole bound state. And this is now a real bond. This is a real bond. It's not a very strong bond, but for catalysis that's perfect, because the somewhat weak bond basically is able to outcompete this bond and pull it off. So the formation of this new bond is basically outcompeting the old CF bond. So we decided to try it this way. We thought, could we think of a repeating oligomerizing reaction with the magnesium that could somehow create at least a nano-sized version of the pentagraphene? And ultimately, we decided not to go for pentagraphene right away. We decided to start with benzene, perfluorobenzene, because it's two-dimensional, it's simpler. With pentagraphene, of course, we need some kind of 3D materials, and that will be more difficult. So we thought about another magnesium reaction, which is well known, which is an electrophilic attack of the nucleophile. And ultimately, this reaction was kind of intended just as a test reaction. We didn't expect to get anything interesting out of this. We just wanted to whet our appetite and understand what we're doing. So the first step of this reaction is, of course, the metallation. The metallation means that we're preparing the nucleophilic site on the benzene ring, right? This is the nucleophilic site. So magnesium couples, bumps the fluorine forward, and now we have an MgF ligand hanging off. This is, of course, electrophilic, and this is nucleophilic. So that's the idea, is we'll try to use the nucleophile to attack another benzene and another fluorobenzene, and we could couple them that way. So why fluorine? Well, surprisingly, the metallation barrier, contrary to what you would expect, is actually less than if you use bromine or chlorine. Less than chlorine, I believe, by actually like a pretty decent amount. I think 5 to 10 kilocal per mole. So this was the activation barrier, so we calculated it with DFT. The long-range corrected functional, which I'll show you. I'll show you our the functionals we tried out in a little bit. So we can see that when we calculate them in solvent, this barrier is not very big, of around 15 kilocal per mole. So it should metallate quite efficiently. And then we see that the reaction is also highly exothermic, so it releases quite a lot of energy. So we made sure to do our due diligence, because unfortunately not a lot of research on this stuff has been done. This kind of reaction has not been investigated very thoroughly. So we basically had to compare with much older calculations where not such great basis sets were available, and the newest calculation we could compare to was ultimately our inspiration. It was this reaction. So we did the calculations, the benchmarking, and we got good results. So Omega B97XD gave us good results that compared well, and this work was also joint work with experiments, so they compared to experiment, which means we ultimately benchmarked well. And of course we benchmarked the methods also. Our benchmark just compared to the composite method, because this was done before we thought of to do benchmark against the previous paper. And when we compare Omega B97XD to the composite method, it performs well. So we can be relatively certain that this method is good enough for this chemistry. And of course, GGA methods, people who work in fluorochemistry know that carbon-fluorine bonds usually do not get reproduced very well by GGA methods, unfortunately. So BP91 didn't perform so well, but we did most of the optimizations with it, because BP91 is actually about as fast as Hartree-Fock in terms of optimization. So in terms of creating the initial wave function, this is a very good functional, and it is also an exceptionally good functional for transition metals, better than most modern functionals actually. So metallation and solvent. Here we actually simulated the metallation with the solvent present overtly as such. So we just wanted to know how many solvent molecules are really needed for this reaction, and it turns out just one. Just one solvent actually solvates the magnesium. The other one is far away, and you can see that the IRC curve, the intrinsic coordinate reaction curve, does not change very much when we add a second one, but it's still kind of an interesting and pretty picture, so we included it in the work anyways. So one molecule is ultimately enough. 1 molecule per 1 magnesium is sufficient. So according to our calculations, we got good news. The THF solvent stabilizes the transition state of the product much more than the reactant. So that means that the reaction will become more favorable in this solvent. So we picked our solvent correctly. Right, that's what I just said. It's going to be a much more exothermic reaction. So there's a few issues involving metallation that we have to think about. Perfluorobenzenes are relatively reactive, but experimentally this has been difficult to achieve. This reaction that we are proposing has been difficult to actually do. The reason is probably because of actually the magnesium source. It's not due to the barrier, but ultimately the magnesium source, and it has been shown that these molecules are more easily metallated by the use of magnesium anthracene. So this issue can probably be worked out over time. So this doesn't seem to be a huge problem. This seems to be an experimental issue. And also, of course, we know, it's been mentioned in the previous talks before mine, that of course metals often catalyze as clusters. Magnesium also does this. It also catalyzes as a cluster. But fortunately, in this case, it has been shown that in THF solvent, it actually becomes atomic. It leaches. But even assuming it is a cluster, the barrier is actually even lower when it clusters. So one of the ways that this reaction could even be further improved is probably by figuring out a way to leave it as a small cluster. So what I'm going to tell you next is actually nothing new. This has been investigated many times over. This is called the Schlenk equilibrium. It was first analyzed almost 100 years ago in 1929, and ultimately all we're looking at here is we have two Grignard reagents, and they do a little dance. So they can couple this way, they can couple many times, they can remove a MgX2, the halogen X2, X is the halogen, and this is all in equilibrium. So ultimately what I'm going to describe next is Schlenk equilibrium just instead for a perfluorobenzene instead of bromine containing compounds as was usually considered by the Schlenk equilibrium. So heterocoupling, of course, means that we couple a perfluorobenzene to a perfluorobenzene, and then it takes off a fluorine and MgF2 flies off. So the curve we generated, again by IRC method, pretty simple, pretty straightforward. The barrier is a little bit higher in THF than metallation, but it's still not a very high barrier. Again, a strongly exothermic reaction, so we can see that the foot here is much lower than our reactant. We also considered, of course, heterocoupling of the Schlenk equilibrium intermediates. So we can see here that this is the bidentate and this is the single bridged. So again, we form this bond here, and here we form this bond. And these vectors that I'm showing you are basically these correspond to the normal vectors of the imaginary frequency of the transition state. Quite a mouthful, but that's what it is. And basically that's how we tell IRC what direction to step in. First we prepare the checkpoint, then we run IRC, and that's how that works. And ultimately we can see what happens here. We form this bond, and then our magnesium containing fluoride flies off. Well, these are a little bit less favorable, so these are higher barriers. And the thing to understand is that the precursor single bridge is actually the more stable one, so this is a 30 kilocal barrier. So this reaction probably does not happen that much. But it's interesting to note that when we consider the charges of the nucleophilic carbon, right, this one, and this one, and this one, we made these little pretty pictures of the ESP surface, and it's pretty much how we'd expect it to look for a Grignard reagent. A lot of charge on the fluorine here, not much charge on the magnesium. Of course, it's donated it all. A little bit of charge on the nucleophilic. And when we use NBO analysis, we look at the charge localized to the carbon prime. And if we plot these carbon primes, their transition state energy versus their charge, we see that, of course, the transition state is lowered depending on how much, how nucleophilic the carbon is, the nucleophilic carbon, the attacking carbon. And this is common sense in organic chemistry, right? The more negative, the better of an attacker it is. So this is common sense, but it's satisfying to see it. So this is probably a result that was not. This was a result that was completely unexpected. We were ready to move on. We understood these reactions, but just because these appear in Schlenk equilibrium, we decided to analyze them. And as it turned out, this was actually by far the most interesting result: the homocoupling of two Grignard reagents. So let me just show you the outline, because this is a little bit complicated, and then I'll go into the details. So first of all, here we can see the coupling, right? This is after it already bumped off the MgF. So one MgF bumps off the other MgF. Then it rips off a fluorine off of this ring, and this is kind of unexpected completely for us. We form an Aryne here. This is an Aryne ring that's floating out here. So we form our Schlenk equilibrium intermediate and an Aryne. And now this Aryne reacts with a nucleophilic carbon. Nucleophilic carbon reacts with the not so charged carbon. And this branch, this Mg2F3 branch, actually transfers onto the Aryne. And it transfers here. So the catalyzing part actually stays on the ring, and it's ready to react again. So that's the outline of what happened. Now we'll go into the details. So this was a lot of work. Initially we sent out the paper with just the pathway 1. So pathway 1, so like I said, we start with Grignard reagents. Two of them, of course, they couple. So these are all coupling products, which I'll show in a moment. But the thing I want to say is we first just said we proposed pathway 1. So pathway 1, you can see it goes through a bumpy road, and then it goes to P1. And we said, well, our molecular dynamics rearranges to P2, so that's good enough. We have product 2. We don't know how we got it, but it's possible. Well, the reviewer was a jerk, as all reviewers are, and he said, you know what, show me how you got P2. Show me the pathway to P2. So that was another 2 months we spent, but we ultimately proposed 2 new pathways, and we were successful, and that made the paper much more interesting and much stronger. So the review process did its job. And the thing I want to say is we can immediately note that this reaction really is surprisingly favorable, because our reagent is by far the most energetically highest point of this diagram. So all of our transition states are much lower than the reagent, and this was a completely unexpected result. And of course, a highly exothermic reaction. Okay, so here are the first steps. So of course so remember we're starting from this. So our Grignard our Grignard reagents couple. They can couple in many different ways. So LM2 is a way where they can couple. So this is kind of a side-on coupling. This is a kind of a ring-to-ring coupling. And ultimately, though, they rearrange into this kind of idiot, very symmetrical. So we have a mirror plane here. So this is this pathway, and this is this pathway. And this transition state was somewhat difficult to prepare. rotary transition states tend to be difficult to prepare, but here it is. We got it. It worked out. Not a very high transition state either. Almost no energy required to rotate, which kind of surprising. You think it would take more, but it takes almost no energy to rotate this this complex. So the next coupling was the most favorable coupling, but this kind of coupling is also the result of LM2, and I'll remind you, LM2 looks like this. It can basically also move over and also couple this way. So this is the classical Schlenk intermediate, and this one has a pretty surprising behavior because it can straight up rip off a fluorine, and this is how our Aryne intermediate, our Aryne product is created. So it's in the intermediate. So of course this is a highly reactive molecule now that we have in solution. And of course we did our due diligence. We did our intrinsic reaction coordinates, and it's just interesting to watch it because we can see it move along the carbon bond and actually rip off the fluorine and actually create the Aryne. So this is what happens next. This is the most important step, of course, the CC bond formation, and here are the vectors again. So these I think this is in the opposite phase. These arrows should be pointing opposite, but ultimately this bond is created, and this transfers over here, and here's our product 2, which we worked so hard for, and there it is. The other pathway is, of course, through LM4. This is the symmetrical intermediate that we have. Again, we prepared a transition state where it rotated out of a symmetrical state into into a state where one of the carbons is now exposed and ready to react. And again, we have in this pathway as well, we have an Aryne forming. So the transition state is again Aryne containing pathway. So we have 2 Aryne containing pathways, and the result is the same, is just a bidentate, but it's ultimately the same as the P2. And as I've noted before, if we put this into molecular dynamics, this will rearrange the P2. So that's the pathways we described. Now I hope I can actually play this video for you. Okay, here it is. So on the right side, I've glued together 2 IRC calculations, and on the left side, you can actually see the molecular dynamics calculation simulation actually work itself through 2 transition states. It actually passes through 2 transition states and ultimately forms the product 1. I'm not letting this reaction run its whole course, but you'll just have to trust me when I say that this reaction will actually reach product 2 if we let it run for another minute or so. I let this simulation run for quite a while because I was curious myself. Very interesting results. So molecular dynamics can really sometimes open your eyes up on other possible products, because I found that if you start from a transition state and actually input energy into the transition state vectors, this is described for the Gaussian program, it can actually often find another saddle point and go through another reaction and reach a different product. So one transition state does not necessarily mean one product, and I didn't really expect this to be the case. So like somewhere around here, like the saddle point or something, we could have a bifurcation of the surface. So we could have more than one product, and basically that's what is going on, is we should be able to get a product 2 as well. And our recent research has shown that this is possible in other reactions. So molecular dynamics, I highly recommend trying it out. This is actually quite an important tool for catalytic chemistry. And of course, we have our IRC calculation, which shows the same thing, but this is, of course, IRC. This is just following the surface. So this will always give just one product. the expected product. So nice animation too. We also did this with the THFs present. We actually put in THFs, and this same thing will happen. So this will happen even when we have solvent molecules in the simulation. So what happened? Well, something incredible happened. Charge transfer happened. So what happens is, first of all, in this intermediate, we have what we expect, right? We have one Grignard reagent, another Grignard reagent, and they both are electrophilic, so they should not be able to react at all. This should not go anywhere. This should be going back in the Schlenk equilibrium. This should go back where it came from, and this should be over. But no, this magnesium is able to rip off a fluorine, and ultimately these separate. So we now have two molecules really, and we only have one Grignard reagent remaining, a Grignard reagent and an Aryne. Now the Aryne is reacted upon by the Grignard reagent, and what happens is the nucleophilic center, the charge center, transfers from free to 1. So now we have a new Grignard reagent. So the charge transfer happened basically free to 1. So as we form the bond of free and 2, we transfer our electrophile onto 1, and we re-prepare a nucleophile. So we've regenerated the nucleophile, we've made a carbon-carbon bond and made a new nucleophile that's ready to react once more. And we thought this was a pretty incredible reaction because we went through literature as carefully as we could, and of course we're not huge specialists in catalysis, but as far as we know, this exact reaction has never been described before. So it was quite a trip that we did, and of course this result seemed so important that we made it our talk, our table of contents picture, because it's quite pleasing to see. It's a nice little picture. So we have just a few open questions about this reaction, and of course the first question is, can we do the same thing with a different metal? And the answer is probably yes, right? And there's a lot of catalysts out there. The second question is probably not as easy to answer. Is it possible to do this with other halogenated benzenes? This requires investigation. Maybe, maybe not. We did try bromobenzene, but we weren't yet successful. So this truly is an open question. And of course, can we actually achieve what we set out to do? Can we actually make a nanophase pentagraphene? Is that possible? And this requires still a lot of work, but hopefully by this kind of reaction maybe we could find something. But of course this reaction is in itself an incredible reaction. It's a very interesting result. So pentagraphene will have to wait. Conclusions. Well, I mean, I think the result speaks for itself. We have an unexpected result of two nucleophiles coupling and creating a new nucleophilic center by charge transfer. And I think the bigger conclusion here is novel results await us in unexpected places. This project has really shown to me that exploratory chemistry really is the most exciting part of this work, I believe. And we often just have to follow the chemistry and follow our interests, and then we might be able to find something truly novel that has not been proposed or seen before. So I acknowledge Purogena for giving me money and inspiring this project and pushing me along, because for a long time I really didn't know what to do with it. Of course, my father and Catherine, they especially helped a lot in making this work look very beautiful, especially the figures. We went through many iterations, so the high figure quality and the very good English in the paper is of course their work. They worked very hard on this paper to help me bring it to a high standard. And of course I would like to thank my late graduate school advisor, Harold Croto, for getting me interested in this project, in this pentagraphene stuff, graphene stuff, really science in general. and really giving me a new perspective on science, because the way he always told it is his discovery, which led to his Nobel Prize, was something small. It was merely just a little peak on a mass spectra. C60 was a peak on many mass spectra, for example in soot, and people had not really paid attention to it. It's a small peak. What difference does it make? And he took note of it. So he was just the first person not to see it, but to take note of it, to think about it, and to follow his interests. And that, of course, led to what we know now as a very, very important, technologically important molecule, fullerene, which excites thousands of researchers today. A lot of research involves it. So it's very important to follow the science and be creative and follow your interests. That's I think his biggest lesson to me. So thanks a lot for letting me talk. I appreciate it, and that's it.